All right, there doesn't happen to be a free response problem like this one in your free response notebook, but it's one way that Taylor series are sometimes tested. So we've been asked to write the first degree Taylor polynomial for h about x equals 2, and use it to approximate h of 1.9, and then decide whether that's an overestimate or an underestimate. So notice that a first degree Taylor polynomial, that means we're going to write the Taylor polynomial that has x to the first power in it. This is just linear, so this is just asking us to write the tangent line approximation, but at x equals 2. So I can write that h of x would be approximately equal to h of 2 plus h prime of 2 over 1 factorial times x minus 2. That has, so x minus 2 to the first if you want to be specific. That's that pattern for writing a Taylor polynomial that you're going to have memorized. So now I can say that h of x would be approximately h of 2 is 80 plus h prime of 2 is 128 over 1 factorial, but that's just 1, x minus 2. So that's worth 2 points for writing that two-term Taylor polynomial. The next part of that question is we're supposed to use this to approximate h of 1.9. So h of 1.9 is, all I have to do is take that polynomial I wrote, which was 80 plus 128 times 1.9 minus 2. I could just leave it like that. I don't have to simplify at all. Obviously you could simplify, but that's my final answer for my approximation for h of 1.9. And the next question is that approximation an overestimate or an underestimate? Well, it's the same question as when is the tangent line to a function an overestimate or an underestimate? So it has to do with the second derivative. If h was concave up on the interval between 1.9 and 2, then my estimate is going to be an underestimate because the tangent line lies below a curve that's concave up. So we're going to go investigate the second derivative of h. So I'm looking at the table. Oh, look, it even says the function h and all 4 of its derivatives are increasing. So if all of its derivatives are increasing, then h prime is increasing, which means h double prime of x must be positive, which means h is concave up. And I would write my conclusion like this. So this would be my answer to the last part of A, is my approximation of h of 1.9 is an underestimate since h prime of x is oops, I misspelled increasing on 1 to x to 3. Now that interval, I only just gave it because that's the same interval they gave me. What I really, really need is to understand the behavior of h prime on the interval 1.9 to 2. That's the critical interval, but here they happen to have told me that it's true for the whole interval 1 to 3. All right, now they want me to write the third degree Taylor polynomial. So I'm going to go through that same process, that same pattern that I used to write my first degree, my 2-term Taylor polynomial. I'm going to do it, but I'm going to take it up to 4 terms, or the third degree. And then I'm going to use it to approximate h of 1.9. All right, so here's what my polynomial is going to look like. You don't have to write out this step on the test, but I'm just going to show so we understand where it comes from. So it's going to be h of 2 plus h prime of 2 times x minus 2 plus h double prime of 2 over 2 factorial times x minus 2 squared plus h triple prime of 2 over 3 factorial times x minus 2 cubed. So I'm going to say h of x is approximately equal to h of 2 is 80 plus h prime of 2 is 128, x minus 2, plus h double prime of 2 is 488 thirds, 488 thirds, over 2 factorial times x minus 2 squared, plus h triple prime is 448 thirds, 448 thirds, which is different. That last one was 488. This is 448. It's going to be over 3 factorial x minus 2 cubed. All right, that's worth probably 2 points. Let's look. That's worth 2 points right there. And then this is a calculator problem you might like to know. To get my approximation for h prime of 9, I'm just going to plug 1.9 in for x in all of those little terms, and I'm going to get h of 1.9. If you use an equal sign, you won't get full credit, but it's approximately equal to 80 plus 128 times 1.9 minus 2 is negative 0.1 plus 488. I'm just going to simplify that. 488 over 3 divided by 2 is 488 over 6. This is going to be negative 0.1 squared plus 448 over 3, and then 3 factorial is 6, so 3 times 6 is 18. This is going to be negative 0.1 cubed. You could leave your answer like this, or you could plug it in. It turns out to be approximately equal to 67.988. All right, and now here's the new part. We're going to use the Lagrange error bound, so that's Taylor's inequality, to show that the third degree Taylor polynomial, the one that we used in part B, approximates h of 1.9, which is what we were trying to find, with an error less than 3 times 10 to the negative 4th. So let's just remember 3 times 10 to the negative 4. That's like 3 over 1 with 4 zeros is one way to think about it. Or less than, that's a 3 with 1, 2, 3, 4. So 1, 2, 3 zeros in front of it. So I'm going to move to the blank screen so I can write up our Taylor's inequality. Okay, so we know that the absolute value of the error has to be less than or equal to m over n plus 1 factorial times the absolute value of x minus a raised to the n plus 1. Since we used a Taylor polynomial of order 3, n is 3, which means here n plus 1 is going to be 4. A is the center of our series, and we've been centered around x equals 2. And then x is the x value you want to plug in. So in this case, it's going to be 1.9. So the tricky part here is going to be to figure out what m is. Capital M, it's the biggest value of the n plus 1th derivative. So that means in this case, the biggest value of the 4th derivative. I'm going to look at my table, and I've been told that h and all of h's derivatives, at least up to the 4th one, at least up to the ones they've put in the table, are increasing. That means the 4th derivative of h is increasing, which means that if I want to figure out its biggest value, I want to look at the right end of the endpoint, the right-hand side of the endpoint. So in this case, that's going to be, and the interval in this case is the interval between the a value and the x value I want to use. So the a value is 2, the x value is 1.9. So the right-hand side of that interval is at 2. So what I want to do is pick the right-hand side of that interval, which is 2, and put that number into the h function, the 4th function, the 4th derivative of h function. And I can see from the table that the 4th derivative of h, when x equals 2, is 584 ninths. So in this case, I'm going to use, for my capital M, 584 ninths. So my error, the absolute value of my error, is less than or equal to 584 ninths times, instead of dividing by n plus 1 factorial, I'm going to multiply by 1 over n is 3, so n plus 1 is 4, 4 factorials, 4 times 3 times 2 times 1 is 24. The difference between x and a, well, the absolute value of the difference is 0.1. So I'm going to raise 0.1 to the 3 plus 1 is 4th power. And I'm hoping that that's less than 3 over 10,000. So again, this is the calculator section, so let's figure it out. All right, so I typed into my calculator, can you see that? 584 divided by 9 times 1 divided by 24 times 0.1 raised to the 4th power, and I got 0.00027. So I would write something like this. Just to write it up in the most formal way, I would say that the absolute value of the difference of p sub 4 of 1.9 and h of 1.9 is less than or equal to 0.000270, which is what I got when I multiplied this out, which is in fact less than 3 times 10 to the negative 4th.